Hello. So let us start the assignment for week 7. Okay. So again, welcome back to the course. So spread spectrum communication and jamming. And jamming. The assignment number 7 is solution to MATLAB code for iterated generation. Of spread spectrum QPSK system. Quadrature QPSK system over additive white Gaussian noise channel, that is AWG design channel. And also assume that Wal-Sadamat code Wal-Sadamat code of length 4 is used for data spreading. Okay. So in the previous assignment we have simulated the BR performance of a BPSK system with respect to SNR gain and EB by N naught gain. So basically in this simulation, in this assignment, we are going to do it the same thing with the particularly with the QPSK system, and the QPSK system is being used as a spread spectrum communication system. So with the wall side mat code that is being spreaded. So the requirements are there. For such purpose, we need to plot of BER versus EB by N naught. Another one is plot of BER versus SNR. So again, these two quantity are different. We think about EB by N naught and SNR type of thing. Okay. So let us go to the MATLAB platform and just try to simulate this particular assignment. Okay. So start with a new script file first, and let us describe what we are going to do here. Starting with it. The code is to find the BR for QPSK spreading. And the channel that is used here is a simple AWGN channel. Okay. So let's first use the CLC, clear all, and close all to remove all the things that we have done in the previous code. So now first define how many samples points we are taking. I mean number of bits that we are transmitting. So that is number of samples. And number of samples equal to, suppose we take 9E5. And this is the number of bits to be transmitted. Then the question has said the length of the wall segment code, the spreading code is 4. So define that here. Length of the code, wall segment code that is being used there is 4. This is length of the spreading code. Now first let us define what is the range, in which range we are just trying to simulate the performance of SNR, sorry, BR with respect to EB by N naught. So EB and N naught in dB. Let us vary it from -2 with interval of 2 to 12. So this is the range of EB by N naught values in dB. Okay, so now start the code. So for the first time we just, here the question said we have to simulate for once for EB by N naught and another for SNR. So we define a variable ACLVAR and we define it as 2 and we define it. This is a selection for plotting VER with respect to EB by N naught. So basically if it is 1, then the plot is with respect to EB by N naught, and if it is the value of the variable is 2, then it suggests that we are plotting it with respect to SNR. That is the whole story for that variable. Now define our variable codemat, and this generates a Hadamard matrix that is being used here of length 4. So basically what it does, it just generate a Hadamard matrix of dimension 4 plus 4, and it just generates the wall segment code from this particular way. So this generates wall segment codes. Of length 4. Now just do a just check what is the codemat here. So this generates a 4 cross 4 wall segment matrix. Now just define two blank arrays that will be used in future to store the spreaded data. spread data and its imaginary part will be stored in the second array. Okay. So basically we are using QPS key here. So there will be infest data and QFS data. So first I data. Let's generate the I data first. 2 into rand. So basically what rand means here, as we have described yesterday in the previous session, it says it generates uniformly distributed pseudo random numbers with an open interval of 0, 1. So basically we are generating a pseudo random sequence by calling this rand function that will call values between 0 and 1, and we will check whether this value is greater than 0.5 or less than 0.5. If it is greater than 0.5, the value it will return this function that I am writing, 1 comma number of samples. This many number of samples were required. So if it is greater than 0.5, the value it will return as 1, and if it is not greater than 0.5, that is a false condition. At that condition it will generate a 0, and basically the values the whole part gets is either 2. If it is 1, it gets the value 2, and if it is a false condition, at that condition it gets a value 0. So either it gets 2 or either it gets 0. So basically after that we put a -1 here. So basically this whole part gets a value either 2 or 0, and if we put a -1 DC value here, that becomes either 1 or -1. So basically in this way we are generating the infest data with either 1 or -1. And so what we have generated, a bipolar sequence for transmitter side. Through the high phase channel. Similarly, there is a quadrature phase data, and this is the imaginary part. So similarly, we can generate the same symbols, like this is also independent of the in-phase data. So basically we have to write the same functions once again. So similarly 1 comma number of samples, and there is a logic check operator, and then there is a -1. What we are doing here, we are generating a bipolar sequence for transmitting through the Q phase channel. Okay. So the baseband signal that we are generating here should be the mixture of in-phase data and J into, that is 1I into Q data. So this is baseband signal containing real and imaginary part. So now this is it. Okay. So basically just check once. If we have 4 samples, 2 samples, based on this, the in-place data could be just print the in-place data and queue-based data. These are the two different data we are sending at one instance, and the baseband signal becomes like this. So it basically marks 1 and -1 first, and then this -1 and 1. So now just define what is the power of the transmitted data. This is equal to summation of absolute value of transmitted data. So whatever the transmitted data, that is x, we are taking mod of x square. Basically mod of x square here is taking. And in the end, we are just dividing by the whole length. So basically it is the sample mean kind of thing. So basically it is the same sequence, mod of x, if x is the transmitted data, then the power is for a particular instance it is mod of x square. So basically if I want to summation it, so it should be x I square and it should be done I number of times if the length of the sequence is I, and then we are just dividing by a factor of I. So this is the summation of all the values xi square for simplification, and then is by I. But what is the transmitted data itself? So just define the transmitted data first. Transmitted data is the Kronecker product between baseband signal and woodmat 3, all. So we have used a Wall-Sadamat code. For such reason, if we take the third row, that will give us a particular spreaded data, and this is the spread data after spread. and n, let us define the length of the transmitted data, the spreaded data, so till this part is okay. So right now we should vary with the particular EV by N naught ratios. So start is for loop here for the variation with EV by N naught ratios. And this is for what? For different values of EV by N naught. And now let's implement the channel. So EB and not the linear scale is, we were taking the dB scale. So basically if we take in the linear scale, it becomes like 10 to the power EB N naught dB, and these values will be varied with each iteration. And it is 10 log 10 SNR. So the first coefficient 10 comes here if we convert it in the linear scale. Basically what we have done here is converted to linear scale. So first, for what we are doing this, there is a condition that we want to plot it with respect to V by N naught. For that condition, we put it ACL BR is equal to 1. So basically, we will calculate with respect to EB by N naught in this. Yes. And the topic that we should remember, code length, as the data is spreaded by one side amount code here. So code length is also included to account the relation EB by N naught. And this EB is basically length of code into EC. So what is the noise here? We just varying the noise with different powers. So EB by N naught. So noise will depend on power of the transmitted data. And square root of length of the code by square root of 2 into EB n naught in the linear scale into random one comma length of the tx data plus the imaginary part. So basically this is the noise. So power is adjusted and according to EB by n naught and length of the code. Otherwise, the noise is square root of our data of the transmitted data. Basically, the first thing was if it was for EB by n naught. If it is not EB by n naught, it should be for S n naught. And in this loop, we are calculating for S n naught. 1 by square root of 2 into EB. So basically for QPSK it is root over 2 EB by n naught SNR. So if we calculate the Q function, there it comes to EB. Basically it EB by root 2 each of the concentration point x. For such region the power becomes SNR, that is 2 EB by n naught. This is 2 EB by n naught linearly into one comma length of tx transmitted data so this is the real part of the noise and imaginary part of the noise is also random coming from a Gaussian distribution, but the powers are defined by this, noise variance is defined by this, and this is a random gives us a normal distribution. So we are calling a normal distribution and just increasing its variance by this following part. Length of tx data. So basically noise power is adjusted according to EB by naught. So just end the loop. So now the data we receive is receiving the data. Received data is something that is the tx data we have transmitted plus the noise so this is the received data. Now let us design the receiver part of the system. Okay. So temporarily the signal we're receiving, let us receive the signal first. And this is for which reason we are just trying to display the spreaded data first. So received data, length the code and length of the received data by length of code. So basically what it does, we are receiving some data and we are just receiving it with based on this particular with a 4 cross remaining matrix. So basically this was a vector and we are doing a reshaping of that vector as a matrix to decode each and every data. So this is for this spreading. The temporary signal is equal to, just take the transpose of data of this temporary signal this is done just for coding simplicity. Now store the size of the temp signal variable. Just store the dimension of this particular matrix that is being generated from this particular data receiving. by signal 1, let us define a new variable, and then what we are doing, it dispreading. Let's cross 1 comma code mat. We had been spreaded it by this particular sequence, so we are using the same sequence here, and this generate periodic code sequence, and then define another variable temporary signal 3, and this does transpose of temp signal into temp signal 1. We just multiplying the spread sequence. Some errors that has been generated due to we are fine with it. Now the disparate sequence is equal to 1 by length of code, the wall settlement code, into sum of temporary signal 3. And this building is completed here. Now the decode signal in the in-phase component is equal to 2 into real part of the disparate sequence. Similarly, we are finding whether it is greater than 0 or less than 0. So this is detection for I-channel bits. Similarly, decode signal for the Q phase data is 2 into imaginary part of the disputed sequence and similarly following this whether it is greater than 0 or not minus 1. And this is the detection for Q channel bits. Now just calculate the error for the I channel first. This is the summation of the places where the decoded signal and transmitted signal in the inter channel mismatch. So this can be calculated with the following code. Decode signal I, and it is not equal to the conditions, how many places it is. I did. So basically what is this? This is error detection for I channel. Similarly, error 2 is equal to error 2 is equal to summation of decode signal Q and its mismatch with the Q data. And this is the error detection for Q channel. Okay, so the total error will be, that is the probability of error in the bits not in the symbols, actually for the bits, because we are counting for the in phase and quadrature phase both the channels. 2 into number of samples. This is the probability of bit error. Basically, the variation with different SNR or EB by NR that depends on ACL here variable is done with this particular for loop. So now we have to check whether there are any error in this code. So basically, the first error is there. Sample check. Close this. So now define the figure, and if we have two defined condition, first is for EB by N naught, second is for S N naught. So if it is 1, is equal to 1, then we should plot semi-log AB N naught TB with probability of error. This is the semi-log plot. X level is EB by N naught in dB, and the Y level is in BER. Otherwise, it should be for SNR. So, as it only else loop, not else if, so that comes naturally. Is semi-log EB N naught TB, the same plot will be there. Probability of error. This is also the semi-log plot, but for SNR. The X level is here, the difference is SNR in dB. The Y level is BER. Just end the if loop here. The legend should be probability of error. And put it on. So for the first time we have defined ACLVAR, that variable is equal to 2. So for 2 it plots against SNR. So the plot it comes with respect to SNR at the first. And we have to increase the number of sample points to get a variation. This will come. So it comes SNR in dB up to 6. Similarly, if we change this variable to 1 for the plot of UV by N naught, it will become error there. Still, this should be power of constant. So this is the plot with respect to v by n naught. It stretches up to 10 or 10 to the power minus 6 with the variation of pv by n naught. Basically, if it is 2v by n naught, that is the SNR in that case. So at that time, we can show with the variation of the variable ACL here as 2. It is for EB by n naught, it stretches up to 10 or 10 to the power minus 5. It is becomes 10 to the power minus 5 or near about value of 7 here. So that is the difference between EB by n naught and SNR with respect to performance of VER. So the conclusion here is the interpretation the VER plots in the figure are different due to impact of code length, splitting of total power, in half for each bit. And the joint effect of the figures, joint effect of the first impact, that is effect of joint effect of first number, code length, and the splitting of powers in half for each bit. Results in a shift of 10 log 10 code length minus 10 log 10. So this becomes 10 log 10 4 10 log 10 2, and it is nearly about 3 dB. So that is the difference between the plot that we observed. It becomes 10 to the power minus 5 DR performance for SNR at nearly about 7 dB. Same thing is observed, but 10 to the power minus 5 is EV by L naught, nearly about 10 dB. So basically, this difference 10 minus 7, 3 dB, is due to this fact. Okay. So these are the two figures. This is the code we have simulated today. So basically what we have done, we have started with number of samples, then we have varied the EV by N naught values and variable ACL here. It takes the value 2, we are plotting with respect to SNR, and if its value is 1, then we are plotting with respect to V by N. And then we have transmitted the data, and then with variation of EV by N naught, we have simulated what is the noise according to that EV by N naught, and then we have received some data, and we have spreaded the data here, and the received data is dispreaded through this function here, and after dispreading we just reconstructed our transmitted signal, that is done by the detection of I channels and detection of the Q channels here, and similarly we have calculated the error in the I channel and error in the Q channel, and for that we have obtained two different error probabilities through the I channel and Q channel. So total probability depends on both the values. So this is the probability of bit error, and after that we have plotted it with the semi-loggy plot, and that was the result. So let's show the results once more. This is with respect to SNR, and if we change ACL here to 1, it will give us the plot with respect to V by N naught. So basically this shows that 10 to the power minus 5 value is obtained at a near about value of 7. That is the point here. So basically this 10 to the power minus 5, this curve will go through and it will come at a value near about 7 that we have described here, 7, and a similar plot for this can be generated for EV by N naught also. And this comes at a value 10 to the power minus 5. So basically that is difference of 3 dB that has been described here. So this is for today. We will meet in the next Tuesday.